This lesson is part 2 of section 7.6. Today we're going to continue to discuss the factor theorem, but now we're going to use our calculators to help us factor polynomials. So I'd like you to pause the video and go ahead and grab your calculator. The objectives for today are 1, to continue to identify the possible rational zeros of a polynomial function. So we continue with listing our possible rational p over q values, just like we did in the previous lesson. And then now we're going to find the roots, though, using our calculator. So let's first start with problem 1. All right, we're asked to factor f of x equals 2x cubed minus x squared minus x minus 3. So the first step we're going to always do is list our possible rational zeros. So we take our p over q values. So we have positive or negative 1 and 3 in our numerator for our p factors. And factors of q are positive and negative 1 and 2. So we end up with possible p over q values of 1, 1/2, 3, and 3/2. So these are all of the possible rational zeros. Now, typically what we would have to do if we did not have a calculator is we would have to test each and every single one of those values to see whether or not any of those end up being zeros of the function. So like I said before, this is a lot of tedious work, but now we have a calculator to help us. So rather than calculate all of this, we are now going to just type that right into our calculator. All right, so as you can see, I've typed in our function 2x cubed minus x squared minus x minus 3 right into my y equals. Now I'm going to graph that so that I can see where this polynomial here will cross the x-axis. So I'm going to hit just graph, but you might want to hit zoom 6 here. That'll take you into a standard window because you might have it adjusted to a previous problem, so your window might be a little bit funky. So I'm just going to go to zoom 6 now. Notice I have an x-axis negative 10 to 10, y-axis negative 10 to 10. Alright, so in blue here is the graph of that polynomial. And as you can see, it's only crossing the x-axis one time at that coordinate here. Now I want to find that 0, so I'm going to hit second calc. I'm going to go down to 0, so scroll down to there, hit enter. It's going to ask you left bound and right bound. So if you want to be left of this coordinate here, right at your 0, you need to be underneath the x-axis, so anywhere underneath, I'm going to hit enter. And then to be right bound means to be above the x-axis here, so I'll hit enter once I get above the x-axis. Hit enter again when it asks you to guess. All right, we end up with a 0 at 1.5. Now what this is saying is that f of 1.5 is equal to 0. And we know that this is equivalent to saying that x minus 1.5 is a factor of our polynomial up here. So once we know that we have a 0, we now have a factor of our original polynomial. Now this is not in a form I really like. Even if I convert that to 3/2, because 1.5 is equivalent to 3/2 here, that's still not in a nice form. Usually when we see factors, this is always an integer, right? So in order to change that from a rational number into an integer, I'm going to use something called the rational root theorem. Now this rational root theorem reads a whole lot like the factor theorem as well. So it states ax minus b is a factor of f of x if and only if f of b over a is equal to 0. So this is just a fancy way of saying something like 3x minus 4 is a factor of your polynomial if and only if f of 4/3 is equal to 0. So this is something that we've done a lot of already. You're used to converting something like this. If you set this equal to 0, you end up with a solution of 4/3. So f of 4/3 then we would assume would equal 0. And that's really that all this this rational root theorem is stating. So when I take a look at x minus 3/2, I can change that into 2x minus 3. So that's the factor that I'm looking for. That's the form for this particular factor that I actually want to use. Now, if I'm going to use synthetic division here to find my remaining factors, what I will do is I will use that 3/2 on the outside here. And then in that case, I will divide out all of these all of these coefficients here in the polynomial by a factor of 2. So instead of 2x cubed, I'm going to call that 1x cubed. So I'll have a 1 in front of that for that coefficient. This negative 1 now becomes negative 1/2. This negative 1 also becomes negative 1/2. And that last constant term is going to become negative 3/2. Let me adjust this bar here. So I'll use synthetic division and I'll carry that out. I'll pause the video. Okay, as you can see, after I took 3/2 here, I do end up with a 0 for my remainder, which means that this is definitely a factor. So 2x minus 3 is definitely a factor for this original polynomial. Now, I'm left over with this quadratic here with coefficients 1, 1, and 1. So I have x squared plus x plus 1. Now when I look at this polynomial, this is actually not factorable. There are no two numbers that will multiply to 1 and add up to 1. So the factors for this particular polynomial here are 2x minus 3 and x squared plus x plus 1. We don't end up with any more factors from this particular quadratic. And you can actually see that if we go back to our graph here, we can see that. See how it's only crossing one point here. It only has one rational 0, and that's the one that we found, the 3/2. Now again, we can double check our answer to make sure it's reasonable. If we multiply 2x times x squared, we end up with 2x cubed, and if we multiply our constants, -3 and 1, we end up with -3 here. So this is definitely a reasonable answer, and this is the factor form of this particular polynomial. All right, when we move on to number 2 here, now I have a quartic, and this has 5 different terms in it. Factoring by grouping doesn't work here, neither does sum or difference of squares. All of those traditional methods of factoring don't work, so I need to use factor theorem here. Now the first step in factor theorem is to list all of the possible rational zeros. So to answer part A, we're going to take all of the factors of our constant term 12 here. So we have 1, 2, 3, 4, 6, and 12. And then for the factors of our lead coefficient, we have 1, 2, 5, and 10. So we're going to have quite a list going here. So I'm going to take this 1, divide it by each of those in the denominator. So I just distribute, well not distribute, but I take each of those and divide it by the number in the denominator. So I end up with positive or negative 1, 1/2, 1/5, and 1/10. Now I'll take 2 and I'll do the same thing. So I'm done with the 1. 2 divided by 1 gives me 2. 2 divided by 2 gives me 1 though. 2/5 is a new term, a new number, so I have 2/5. 2/10 gives me a repeat of 1/5, so I won't write that one down. So I'm done with 2. Move on to 3. 3 divided by 1 is 3. 3 divided by 2 is a new rational number, 3/2. 3 divided by 5 is another new one, 3/5. 3 divided by 10 gives me another new one, a unique one, so 3/10. Now I move on to 4. So you can see this is pretty boring, but I have 4 over 1, which is 4. 4 over 2 is a repeat. 4 over 5 is brand new. And 4 over 10 is a repeat of 2/5, so I'm done with that one. Then I take 6, and so on. So I'm going to just finish off this list real quick. Okay, so as you can see, the only remaining possible rational zeros are 6/5, 12, and 12/5 after I take 6 and divide it by each of the terms in the denominator, and 12 dividing it by each of those numbers in the denominator as well. All right, now instead of testing every single one of those, because look at that, that'd be an insane list to evaluate f of 1, f of -1, f of 1/2, and so on. That would be horrendous. You're going to use your calculator here. So we're going to type into our calculator this function that we started with. Okay, so I type into my calculator that function, and I'm going to go ahead and graph it now. As you can see, it's going to cross 4 different times on that x-axis. Now, when I try to find a 0 of this function, I'm just going to hit second calc down to 2, this 0. And when I start finding the 0 here, let's see, I'm going to hit left bound, so I'm trying to find and locate this particular 0 here. So I'm underneath it, I hit enter. Now I'm going to get above it, I hit enter. And when it asks me to guess, I'll hit enter again. Now this 1.618034, this is not a rational number that I immediately recognize, so I'm going to not use this particular 0. Okay, so when you get an output that you're not quite sure of, or you get an x value that you're not quite sure of, I just try to find a different one. So now I'm going to search for the next one right next to it here. So when I ask to calculate the 0 here, I will go left of this coordinate, which means I'm actually above that point here. So if I'm at this point, I want to go to the left of this point on the function. I need to be above the x-axis in this time. So I'll hit enter, go below the x-axis, hit enter. When it asks me to guess, hit enter again, and now I get 0.8. So at least f of 0.8 is something I can recognize. So f of 0.8 is equal to 0. We're going to come back to that in a second, because you might not have gone after the first, that particular point like I did. You might have gone over and tried to find the zeros here. So let's show you what you would do if you try to calculate those. So I'm going to do second calc 0 again, and I'm going to scroll over. So I want to be left of this coordinate, which is going to place me underneath the x-axis. Hit enter. To the right, I need to be above. Hit enter. And again, I end up with a point here, negative 0.618034. That's not something I immediately recognize. That decimal might not pop out at you right away, but that's another 0, so I'm going to use a different value. I'm going to hit second calc one more time, go down to 0, And now I want to find that particular 0. So I'm going to go left of that coordinate, which means I'm above the x-axis, hit enter. Go below the x-axis now on your right bound, hit enter again on the guess, and now we have a 0 at negative 1.5. Okay, so we have f of negative 1.5 equals 0 as well. So that 0.8 is really the same as 4/5, and this negative 1.5 is the same as having negative 3/2. Now you don't have to find 2. In fact, you only need to find 1. So I just want to show you though how you can use either of those to start. Now I'm going to pick the 4/5 since that's the original one that I went with. So I'm going to take that 4/5 and I'll place it outside of that synthetic division bar. And then when I remember to put my coefficients here, I have to actually divide each one of these coefficients by 5. And the reason why I need to do that is because f of 4/5 equaling 0 implies that x minus 4/5 is a factor, and because that's not in our typical form, we change that using the rational root theorem to 5x minus 4. Now again, 5x minus 4 then is really our actual factor, and if we want to use synthetic division, we have to divide that all by 5, which means we have to divide all of our coefficients by 5. So that's just an application now of when we discussed synthetic division prior to this in that other lesson. So if you need a refresher on that, make sure you watch synthetic division again. So anyhow, I take my coefficients and I divide them all by 5. So I have 2, negative 3/5, negative 29/5, 1, and 12/5. So again, I'm just dividing each of these numbers here by 5. Now I'm going to do the synthetic division with you because I think this is a little trickier dealing with the fractions. So I'm going to drop that 2, and then I'll multiply 2 times 4/5, and I get 8/5. Now when I add negative 3/5 and 8/5, I end up with 5/5, which simplifies to 1. When I multiply 1 times 4/5, I end up with 4/5. And when I add negative 29/5 with 4/5, I end up with negative 25/5, which is simplifying to negative 5. And then when I multiply 4/5 times negative 5, I end up with negative 4. And if I add here, I end up with negative 5. Or I'm sorry, negative 3. So 1 plus negative 4 is negative 3. Then when I multiply negative 3 times 4/5, I end up with negative 12/5. Okay, so I do get a remainder here of 0, which means in fact that 5x minus 4 is definitely a factor of our polynomial. Now after I use synthetic division, remember I'm left with a polynomial that is 1 degree less than the original. So this represents the coefficients of a cubic polynomial, 2x cubed plus 1x squared minus 5x minus 3. So again, I am going to use the factor theorem here one more time to try to continue to factor this guy. So as you can see, anytime you have something into a higher degree, you just continue to use factor theorem until you get it down to a quadratic. So after I use factor theorem one more time here, I should end up with a quadratic that I can easily factor, and I won't need to use factor theorem again. So I'm going to go back to my calculator now, and I will type in this particular cubic function down here. So I no longer will use our original quartic polynomial. Alright, so I've typed in that function now into my calculator. I'm going to hit graph, and I'm going to find all of those x-intercepts. Now, when I calculate these x-intercepts, and I find those zeros of the function, I'm going to start way out here on the right-hand side. If you go left bound and right bound and hit enter here, that number is actually the same number that I remember from our quartic polynomial when we originally started with that. So that's, again, something I don't immediately recognize, so I'm not going to use that one. So I'm going to try to find another one. I'm going to go to the 0 here, and I will go to this second one that's closest to the x-axis here, right there. And I'm going to hit enter above it, and then enter below it. And here I end up with that same exact value. That's kind of strange. So if I hit second calc this time and go to another 0, I end up with, calculator takes longer. Alright, here we go. That 0 is the same 0 that we found for that quartic, okay? So what this is telling you is that you can find 1 0 right away, but the remaining zeros of this particular cubic have to be the same zeros that you would find after taking out that 5x minus 4, after factoring that. You'll be left with this polynomial here, which would have the exact same zeros as the original function, okay? So when we found that x equals negative 3/2, we could have also used that and use synthetic division. So I'm going to now take this polynomial here and use the factor x plus 3/2 would turn into 2x plus 3. So I'm going to use that factor now and use synthetic division here. So let me erase. Again, we're taking now negative 3 halves, placing it on the outside of the fraction bar, or the synthetic division bar. And we'll take the 2, the 1, the negative 5, and the negative 3 here, and I'm going to divide all of these by 2 this time. So I have 1 half, negative 5 halves, and negative 3 halves. Alright, so I use the synthetic division here, and I end up with a quadratic polynomial. I know that this is a remainder of 0, which means that this is definitely a factor of both this function and this particular polynomial function as well. So anyhow, these coefficients give me the quadratic x squared minus x minus 1. Now, this quadratic is not factorable. So I've given you a couple problems where we see that they're not factorable any further, and that's okay because you'll run into that kind of question too. But basically, if that was factorable, we would continue to try to factor this. But since no two numbers multiply to negative 1 and add up to negative 1, that quadratic can no longer be factored. So the reason why we saw these crazy values for that intercept here and that intercept is that they're not rational numbers. So remember, when we factor, we're trying to find rational values so that we can put here, and we don't end up seeing those rational values, so we have to find a value that is rational. So you continue to search for zeros that give you rational numbers that you can recognize so that you can turn them into factors. So anyhow, to answer that final question here, the factors of our original quartic polynomial are 5x minus 4, 2x plus 3, and x squared minus x minus 1. So these are the factors of our original quartic here to answer part B here to factor this polynomial. So I know this is kind of a lot of steps, but we're going to get better and better at it each day. So I'd like you to try problem 3 on your own and check with the key. In case you don't feel comfortable though, I will continue to actually solve this problem as well with you. So I will factor this polynomial with you, but I would like you to try first to check with the key, and then if you get it right, you obviously don't need to watch the rest of the video. Alright, to answer part A here, to list all the possible rational zeros, I'm going to take my P over Q values. So I have factors of P, which are 1 and 3, and factors of 12, 1, 2, 3, 4, 6, and 12. So my possible rational zeros are 1, 1 half, 1 third, 1 fourth, 1 sixth, and 1 12th. And then that takes care of all the 1. Now I divide out the 3 here by all of these in the denominator, and I end up with 3 halves. The 1 is repeated, 3 fourths is a new value, 3 sixths is repeated again because that's 1 half already, and 3 twelfths is the same as 1 fourth. So this is the complete list here. I need to make sure I have that positive and negative out in front. So that's part A. Alright, now for part B, we are going to factor the polynomial completely. So we're going to use our calculator here so that we don't have to take and evaluate f of 1 and negative 1, f of positive 1 half, and negative 1 half, because that would take forever. So we use our calculator to help us out. So I went ahead and I typed in that function already, and I'm going to graph it. Now I have 3 distinct zeros, so I want to see if any of those are rational zeros. So I'm going to hit function, our second calc 0. Let's find that one since it popped up first. Let's find this one here. Left bound of this point means above the x-axis, right bound means below. And I'm going to hit enter here so that I end up with a 0 at negative 0.3333. Okay, this 0 was actually the same as negative 1/3. So I have f of negative 1/3 equaling 0. So by the rational root theorem, we know then that 3x plus 1 should be a factor of this particular polynomial. So what I'm going to do is use synthetic division. I'll start with that negative 1/3 on the outside here. And again, because we are trying to use this as our linear factor, we need to divide everything by 3 in our coefficients here. So I'd have 4 16/3, negative 5/3, and negative 1 here for the coefficients. So I'm going to drop down that 4. Multiply here, I get negative 4/3. 12 thirds is going to simplify to 4. Multiply here, and we get negative 4/3. That gives me negative 9/3, which is negative 3. Multiplying here, I end up with a positive 1. Negative 1/3 times negative 3 is positive 1, and then I have a remainder of 0. So I end up with this quadratic here, 4x squared plus 4x minus 3. Now this quadratic is definitely factorable, so we can factor 4x squared plus 4x minus 3 using splitting the middle term, because I need two numbers that multiply to negative 12 and add up to 4. So I have 6x minus 2x minus 3 now, so I just split that middle term into 6 and negative 2. So I take out a GCF. And I have factors now of 2x minus 1 and 2x plus 3, which means that the original polynomial here, this cubic polynomial, factors into 2x minus 1, 2x plus 3, and my original factor here that I used in synthetic division, 3x plus 1. So again, please don't forget about this guy. A lot of people do. But you can always spot check your final answer. Remember to multiply all of these terms. Make sure that they multiply to your lead coefficient here. And we do end up with 12x cubed, so you can check everything here. And then the last terms here should multiply, negative 1, 3, and 1 should multiply to this constant term here. So that's definitely a reasonable answer. Now let's say you did not choose to use this first 0. Let's say way back here in the calculator you chose maybe this 0 over here. Well, even though you picked a different value for this, you'd end up using synthetic division. You'd end up with a quadratic that can factor, but your final result should be the exact same as mine. So it doesn't matter the order that you chose to factor it into, you'll still get these 3 distinct factors if you use the factor theorem and you use your synthetic division correctly. So let's just say that in your calculator you found this 0 first, that negative 3 halves. Then you would use negative 3 halves on the outside. You'd only be dividing this by 2 then, but you would end up with a quadratic that would factor into 3x plus 1 and the 2x minus 1. Or let's say you use this positive 1/2 here, then you'd be placing a positive 1/2 on the outside. You would factor, and you'd end up with a quadratic, you'd end up with a quadratic that would factor into 2x plus 3 and 3x plus 1. So in either case, like I said, it doesn't matter which of the zeros that you choose, your final result should be the exact same as this. Okay, tomorrow we'll get a lot of practice. Make sure that you feel comfortable asking questions, so watch the video again if there's certain parts that you need to go over, and address those questions with me tomorrow. Nice job. I'll see you in class.